Hi, so this video will be the first one of two that are reviewing linear elastic fracture mechanics. This is based on some slides I had made to review for the final last year. So there's two general ways to formulate fracture mechanics. You have the energy release rate, which is what Griffiths originally derived in 1920, and the stress intensity factor, which is from Irwin. And the difference between the two, they're both related to each other, but the energy release rate is about how much, when you advance the track by a little bit, delta A, like for example, if you have a track here and it's like, um, this is A, and then you advance the track just a little bit, you have like this change in A. It's about saying how much energy is released per that change in track length A. And the problem with that is once we start getting into this, how to calculate a thing here, we can either, for elastic materials, we can do these two things. We can either minimize the total potential energy, which is the external work minus the internal work, or we can use the change in the compliance. As the track gets bigger, the material gets more and more compliant. Like imagine you have like a plate with a big hole in it. That's going to be a lot easier to pull on than a plate that doesn't have a big hole in it, basically. And or you can use what's called the J integral, which we don't have to talk about, but basically it's like if you integrate around far from the track tip, you can get the energy release rate, and it's always elastic far from the track tip. And of course, that's not ideal in some situations because we really only care about the intensity right here at the track tip. So that's what the idea of the stress intensity factor is we're looking approximately for this, and rather than having all of this material dependence where we have to worry about whether it's elastic or not, we just have this geometric dependence right here on this factor F. And so you don't normally calculate F, you just get it from the table. Like, so we have the, my face is covering it, sorry, but we have, we have the data book that Professor Daly provides, and you got to remember to print it out and bring it to the exam. And it has a bunch of different values of F for different geometries. So just to restate that again, energy release rate is about the energy released as the track advances by delta A, versus stress intensity factor is entirely about how much stress is concentrated near the track tip, and it's about the geometry. All right, so we'll do an example problem on this one on the energy release rate. So this one is the double cantilevered beam. So this is a little bit tricky, but it's actually not as bad as it looks. It's very similar to the stuff we did in class. So what this is two beams, and they are fully connected right here, and then they are not connected in this part A. And basically, we're going to try to get the energy release by saying, well, if this was delta A longer, how much would the energy change? This beam, like the beams are being held down right here, so they can't displace, and they're being pulled from the top by P. And what's going to end up happening is they're basically going to bend. This is going to be a really bad picture, but bend like that, and this one kind of will end up sort of being like this. And so when they do that, they're going to open by some displacement. And so we're going to try to figure out what that is. So first, what's the total potential energy? This is the opposite of the way that Professor Daly defined it in class. She used W minus U. So sorry about that, but just so you know. And so this is the internal energy, this 1/2 PQ, and the external energy, this PQ. And so you have to subtract them. Basically, like you pull on something, energy gets stored in it elastically. And so you want to get that elastic energy and the energy by the actual forces that are pulling on it. But those two are related to each other, so you don't want to double count them. And that's why you end up subtracting this. So this is the actual energy that's stored elastically. So then what's the total deflection of the beams? So this delta here, or I guess this is Q, and I called it 2 times delta. Where this comes from, I wish I had an extra animation thing here, is there's some formulas like from ME15. This is your my over I basically, except it's in terms of forces and displacements. So right here, that's your I, and then you have some like elastic modulus. If you have a problem like this, which you wouldn't on the exam most likely, but there is one later on in the homework, I think, you just sort of Google the formula for deflection of a beam. And then in this case, we're multiplying it by 2 because it's 2 beams. So we have that, the Q, and then it's pretty easy from that point. You just, we're going to get the energy release rate. So we're going to do minus 1 over the thickness times the derivative of this. And again, the way she did it in class, it's actually 1 over b d w minus u. And so that takes care of the minus sign difference. So again, sorry about that. But it's literally just taking that derivative. And once you do that, boom, boom, that's the energy release rate. So yeah, this is a very abstract way to think about it, but big picture, the concept is if the idea is thinking about if this track A were just a little bit longer, how much would that change the energy of the system? So I'm going to end this video here and start another one to talk about stress intensity factor, which is a lot more useful in practice.